and thank you all for joining us today for today's ASCE Texas Section webinar titled Greenhouse Gas Reduction Opportunities. If you're not a member of ASCE or the Texas Section, I really invite you to become a member so that you can benefit from being part of this professional organization and all the gratifying and meaningful volunteer opportunities it offers. Now I'm pleased to introduce the presenter for today's webinar, Kathleen Smits from Southern Methodist University. Kathleen Kate Smits is a professor in SMU's Lyle School of Engineering, serving as chair of Civil and Environmental Engineering and Solomon Professor for Global Development. Prior to SMU, Kate was a professor at UT Arlington, an associate professor at Colorado School of Mines, and an associate professor at the U.S. Air Force Academy. She has served as a civil and environmental engineering project manager in the U.S. Air Force, including various deployments, and is currently a lieutenant colonel in the U.S. Air Force Reserves. Kate's research interests are focused on energy and the environment, with applications to natural gas leakage, the cleanup of contaminated soils and waterways, and the storage of renewable energy. Much of her research looks towards the development of tools and models to better understand such systems. Kate teaches courses in environmental cleanup and in developing communities, contaminant transport modeling, and water resources, and other topics that align with furthering research in these areas. And with that, I will turn it over to Kate.
Great. Thanks, Chris. Thanks for the nice introduction and the opportunity to come and speak today. I really appreciate it. And I'm going to share my screen here. Can y'all see my screen?
Not yet. There we go. There we go.
Good deal. All right, so as Chris mentioned, I'm going to talk about greenhouse gas reduction opportunities through detection and quantification of below-ground natural gas pipeline leaks. And this is a topic I've been thinking about and had the opportunity to do research on for about the last decade. And I want to talk some big picture ideas that we've developed, and some research findings that we've had over the past couple of years, and where I think greenhouse gas reduction opportunities are going, and how we can continue to make progress on reduction. And before I get into that, I want to give a shout out to our students at Southern Methodist University. So if you're ever up in the DFW area and you'd like to stop by and check out our civil and environmental engineering program, please do. We have some great students at the undergrad and grad level. A lot of them are involved in ASCE. This is the ASCE Steel Bridge competition this past spring that our students participated in, and we have them go to meetings in Dallas and sometimes over in Fort Worth, and would love to have you connect with our students as well. So we're trying our best to develop innovative engineering leaders coming out of our program. And I think our program aligns pretty well with the ASCE vision that we have, the Vision 2025, where we're trying to develop master builders and environmental stewards, innovators, integrators, managers of risk and uncertainty, and most importantly, leaders that are able to shape the future of engineering in our society. We're not able to get them all the way there, but I think our program puts them on a good trajectory to be able to do that in their career. So we always appreciate our connections to industry, and thankful to ASCE for their support over the years with our students, and would encourage you to participate as well with them should you be around and in this area. For my research, I'd like to acknowledge the funding agencies that have funded this work that I'm going to present today. It's mainly funded through the U.S. Department of Transportation, PHMSA's program, that's the Pipeline and Hazardous Materials Safety Administration, as well as a grant from the Department of Energy's ARPA-E program Parts of the work are also sponsored by the Northeast Gas Association, the Colorado Oil and Gas Conservation Commission. And this is a picture of my research team that is co-led by Dan Zimmerle, who's a research scientist at Colorado State University, as well as my postdocs and PhD students that are listed there. So the motivation of my research is to provide answers to questions of importance to food, water, energy challenges. And as I've written here, that we have this demand for food, water, and energy that it's always increasing. We have the availability of land for agriculture. It's either stagnant or in many cases it's decreasing. And the amount of precipitation that we have is constantly changing. And what is increasingly apparent in these challenges is the use of our precious resources for one need is inherently linked to other needs in this food, water, energy nexus. So this is a picture of hydraulic fracturing and water stresses map in the United States. And as we can see, where we have hydraulic fracturing and where we have the greatest stresses on our water, those are very much co-located. And issues like this and others has really led to my research direction and my thinking, trying to address from a big picture perspective the two questions that I have listed there. So first, how do we weigh the needs of agriculture, energy production, and water use? And then number two, how can we really shift our thinking, our current silo thinking about either food or water or energy, and look at this more in a nexus approach? So my work up to now has been focused on these food, water, energy issues that have to do with interactions or exchanges, mostly between the land and the atmosphere, or with water and land. And so this can be applied to many different issues. So I've looked at, as Chris was talking about at the beginning, environmental cleanup, so environmental remediation, and of course, agriculture, but more specifically, irrigation planning and understanding surface salinization in different agricultural settings, looking at energy storage in shallow subsurfaces and how we can do that more efficiently. My work's been in landmine detection and how we detect buried objects more effectively, and then some other ones there. But going back to my motivation, our capacity to understand all of these systems and look at whole systems is really predicated by our capability to understand the various elements of each one of these systems and their interactions. And so today I'm going to talk specifically about greenhouse gas reduction opportunities through detection and quantification of natural gas pipeline leaks. But I think a lot of my approach that I take to this work, you'll see, could also apply to many other research applications as well. So being from the military, we have a phrase, and many of you have maybe heard it, bluff or bottom line up front. So if you take anything away from this webinar today, I think it's pretty much listed on this slide. So first, why we even care. Underground, what I'm calling anthropogenic sources of greenhouse gas emissions, they're very significant, and I'll show you that in a minute. And many of them remain undetected or unresolved for long periods of time. And a lot of the emission work that we've done up to date is predominantly on what I call above ground infrastructure. And so these are the stuff that's sitting above ground that we can see. And so the below ground work that has been done to date has been on very large emission sources. So these large emitters, sometimes you'll hear them called super emitters. So these are things that are emission sources that are upwards of 100 standard cubic feet per hour. And this makes sense that we've focused on these big emission sources, because when we show progress and demonstrate early success on these large emission sources, this helps get more stakeholders, especially industry, on board with emission reductions. But we can't just hang out with the low-hanging fruit. We need to focus on the hard part of emissions, which will require a different approach. And therefore, we need to develop different tools or amend tools that we already have. And that requires more focus on that research part to try to get these breakthroughs, and of course get them into the marketplace, which is a whole another beast in and of itself. So what my research group is trying to do is develop innovative ways that we can locate, monitor, and mitigate fugitive greenhouse gas emissions that are associated with either existing or emerging underground energy infrastructure. So we're focusing specifically on the not low-hanging fruit. So these below ground sources that are smaller sources that a lot of times persist for many years or go undetected. And we're focusing on multiple greenhouse gases, not just a greenhouse gas by sector. So this can include, for example, natural gas leakage from a pipeline, and the main component of natural gas is methane. It's typically 85% or more of methane. We can also look at greenhouse gas emissions from carbon dioxide. Here in Texas, we have an increased infrastructure and pipelines for CO2, so that we can use so we can pipe the CO2 to the sequestration and storage sites. We're also looking at hydrogen and then other greenhouse gases such as fluorinated greenhouse gases, and specifically sulfur hexafluoride. The sources of these, they include a variety of anthropogenic sources. So this can be oil and gas infrastructure. And so my talk today is going to be around what my work up till now has really focused on, which is pipelines and wells. But we can also apply this to transportation and storage infrastructure for hydrogen and captured carbon dioxide. And then I mentioned sulfur hexafluoride because I think it can ultimately be applied to electrical transmission lines and others, for example. So how do we do this? So we're looking at different system level solutions to detect greenhouse gases and try to detect them in those lower ranges. So as opposed to the big emitters at 100 standard cubic feet per hour, how do we get those smaller ones? And so I think the first step in this process, and what I'll go through a lot of today, is first, what do we understand below ground? So when we have a leak, for example, from a pipeline, how does that leak behave? And then after that leaked gas gets to the surface and then into the atmosphere, and then ultimately, how can we use this understanding to advance our leak detection and our quantification solutions? So first, looking at sector trends in greenhouse gas emissions, this is from the US EPA inventory of greenhouse gas emissions, and this is showing sources of greenhouse gas emissions by sector. So it's showing industry, electricity, transportation, et cetera. And then when we start to break it down, we look at different, different industries. So this one showing fossil fuels versus natural gas systems, chemical production, et cetera. And many studies predominantly focus on emission types by sector, like you see here. And so this results in a very general understanding of the primary sectors and the primary greenhouse gases from this sector. So it's a very bean counting approach. What if instead of looking at greenhouse gas emissions by sector, we looked instead at greenhouse gas emissions by location, regardless of the source? And by doing that, we may be able to mitigate those emissions more holistically. So these are some pictures I grabbed off of a quick internet search of looking at greenhouse gas budgets. And it shows a global carbon budget, for example. And then it just shows that one's from a paper just showing different sources of emission into the atmosphere. And what you really notice from all of these figures, and if you went and did a similar look on the internet, you'd see these figures too, is they're predominantly thought of as above ground issues first and foremost, but also an issue that is in the atmosphere, as opposed to looking at it from a below ground perspective. But I think that we have an opportunity to address emission sources in parallel, as opposed to just bean counting some of these, because many of them are from below ground sources that if we try to capture the emissions and an understanding of the emissions at the source, we can do that a lot more effectively. And I'll explain a little bit how in a few minutes. So going back to the EPA's inventory, if we look only at below ground sources of emissions, we can start to potentially see different opportunities for innovation here. So dialing into these below ground anthropogenic sources it shows that, and this is just Kate's estimate based off of the US EPA inventory, we have about 75 that MMT is million metric tons of CO2 equivalents of emissions from different below ground sources. And so if we applied this to a cost factor, and there's different numbers out there, I'm not trying to debate the numbers of what they are, but one example is from a group called Carbon Negative Earthshot. And what they're trying to do is apply a dollar amount to all of this and trying to capture carbon in the air at less than $100 a ton, I think is what they're trying to do. We're talking about billions of dollars. So that 75 MMT would be something like $7.5 billion annually of emission reduction opportunities from below ground sources. So dialing into below ground sources here, what this figure shows is an underground pipeline leakage and how that can result in gas buildup and ultimately migration through soil. And then after it migrates through the soil, it releases into the air or into a substructure. And so this results in, of course, environmental health and in safety issues. So what we understand from a below ground perspective is that the leak is highly influenced by environmental conditions. So in the subsurface, we have different soil heterogeneities, we have competing utilities, and we have differences in soil moisture, which is all changing the pathway that the gas can flow. We also have the thermodynamic properties of the gas itself. So varying gases vary in density and viscosity, and that affects their transport behavior. Then when we get to the surface, as you can see in this figure, the surface could be blocked because of pavement, or it could be open to the atmosphere, or there could be some sort of seasonal change on the surface. So from rainfall or possibly from snowpack or ice. And then after the gas gets into the atmosphere, we of course have additional variance with the meteorology. So changes in the wind condition, the stability, the cloud cover, recirculation of the atmosphere. What is common to most pipeline incidences that occur is there's a lot of complexity and there's a lot of unknowns, like you see in this figure, which makes finding below ground leaks really, really hard. To add to this, to date, there is no standardized protocol available for considering all of these factors that I just mentioned in our data analysis. And so this, again, it results in leak detection and leak quantification for these below ground leaks being difficult. But when we add to this complexity, different methods for leak detection, what we see is that no single method can find all leaks. And this has been shown in multiple studies that have been done. There was a study by a group out of Washington State led by Brian Lamb, another one out of Colorado State University by Weller. And they were looking at driving and walking surveys on pipeline leaks in cities and really saw different subsets of emissions being caught based on the mode of detection. And so these different methods are finding different leaks. And of course, we have, like I have listed on the slide there, partitioning of these methane emissions, difficulty in the source identification, and then the representative of the measurement. So looking at different temporal and spatial coverages, as you see in the picture that shows these bottom up versus these top down methods for leak detection. And then finally, what I think adds to the complexity of leak detection for below ground leaks is the lack of integration of these methods. So we have these top down and these bottom up approaches, and the integration of them is highly lacking. And I think the main point that's missing is how to understand what detection capabilities are really needed, depending on, I guess, what I'll call the nature of the underground leak, and then the variation in the work practice when someone's trying to detect a leak. So there's a lot of uncertainty in this overall process. So the objective of a lot of my work is to first understand the gas transport behavior and develop methods to predict the conditions needed for the gas migration to occur, and then how we can understand how to work that into recommended practices to improve our response to below ground gas leak incidences. And so how do we find the leaks and how do we fix the leaks ultimately is the goal. I'll also talk a little bit about quantifying the leaks, but ultimately the goal is to find the leaks and to fix the leaks. The quantification piece is becoming more prevalent with some of the changes to the Pipes Act that are coming down the pipeline, for lack of a better term, that are going to require under certain upstream, midstream, and downstream operations to do some leak quantification as well. So the approach to my research is threefold. So my work, it really moves between looking at modeling as a tool in order to answer different questions, running different controlled experiments, either in the field or in my laboratory, and then working with operators to apply what we've learned to the field. So, and that includes working with oil and gas companies, as well as first responders, and in some case, technology developers to test different theories that we have. For this work that you see right here, this is showing one of our experimental sites at Colorado State University. It's called the Methane Emission Technology Evaluation Center, and it's run by Dan Zimmerle's research group, and my group operates the pipeline testbed at this site. And so what we have at this site is a series of below ground pipelines that leak at controlled rates, and we can then monitor all of that below ground leakage in the ground and then on the surface and then in the atmosphere above. So it's an 8-acre site that has, I think, about 50 controlled leak points below ground. And then the subsurface is instrumented with both environmental sensors, so we can monitor our soil moisture, the pressure, temperature, humidity, etc. But then also with natural gas sensors that can monitor our methane concentration continuously and over space and over time below ground. Then when we look at the surface, we also have some different sensors that we've developed that can take our surface concentration measurements, and then a variety of sensors that you can see mounted on different tripods and such. One of my postdocs is setting up an experiment here where we can measure our gas concentrations as well as our meteorological conditions above ground. So to my knowledge, this is the only site that we have in the country that we're able to get the below ground profile of the gas leakage, the surface profile, and then the above ground concentration profile, and link that with an understanding of the environmental conditions. And so what that allows us to do is advance scientific finding, to advance our engineering practice when it comes to leak detection and quantification, and then also how we can advance our technology at the same time. So it's a really unique site that we can really jump back and forth from more fundamental research to more applied research because of the applications. So to give you an example of this, I'll show you some sample experimental results that we have. So this is showing gas leakage behavior above and below ground and on the surface for some representative leak event. So I think this one is for like a 2 or 3 standard cubic feet per hour leak. And so if we look at these top charts up here, that's A through C, this is showing our atmospheric profiles. So if you look at B, for example, this is showing methane concentration with height above the ground. And so in this talk, I'm going to jump a bit around between above ground and below ground, but I'll try to really emphasize that so you understand what we're talking about. And with the study that we're doing that's published in Environmental Science and Technology, what we were showing is this substantial dissipation within the boundary layer right above the ground, even at low wind conditions for big leaks. And so the industry practice, there was a bias towards, well, even if you have a really big leak, you'll be able to see it with a not very sensitive instrument above ground. But what our work was really trying to show and do it very systematically. So look at it for small leaks, big leaks, and try to develop our concentration profile was what would be our minimum detection limit for scenarios like this. So what we showed was when we have a relatively large below ground leak that we'll see 90% by volume right on the surface, and that will go to around 0.01% by volume, just a couple of centimeters above the ground surface. So small atmospheric concentrations, the whole point being, do not equal small leaks. And for those of us that understand that the atmosphere is this huge sink, that makes sense that, yeah, you're going to get really small concentrations when you're trying to measure them in the atmosphere. And so as a result, a lot of my work then has shifted towards, instead of trying to find these really small concentrations in the atmosphere, why don't we instead try to find big concentrations on the surface or below ground? So if you look over to the left here, where it shows these surface concentrations, this is just one example of a surface profile of a natural gas leak that we were initiating. And what we were able to do is to build a detector, a relatively cheap detector that we can place on the surface, or we can place right below the ground, to be able to get those concentrations with space and time, and then use that to estimate emissions. So we came up with this work, a new method for estimating underground leakage rates using these surface concentration measurements and a couple of soil properties that are easily obtained from industry. So if industry is doing some sort of walking survey or driving survey, then they'd very easily be able to get this information. And then the below picture, where it says below ground concentrations, what this work was showing is the dominance of different transport mechanisms. And this one specifically was showing the dominance of soil moisture, even more so over soil texture, on the natural gas transport behavior. And this work was important because we're trying to resolve the different parameters for that gas transport behavior and how we can then work that into our leak detection initiatives that are done. So we're really showing that in this work, the effect of soil moisture is very important. Going back to the surface concentrations, I'm going to move now to look at how the atmosphere affects the concentrations that we're seeing at a surface. And so with this work, what we're trying to do was establish a constant below ground leak rate and then measure at 40 different locations above a known leak point the gas concentration over time. And as you can see in this chart that's plotting the time versus the methane concentration, the surface concentrations increase as much as 4 times during low wind, high stability conditions. And so that was happening during the nighttime compared to the daytime concentrations. And so the leak rate's not changing, but the surface presentation of that leak is changing. And so when we take this information and we work it into our algorithms that we have to calculate emissions, what we showed was that larger leaks during sunny, windy conditions, they actually end up looking like a small leak. And a small leak during stable, low wind conditions look like a big leak. And that can be seen with the purple line and the red line right here, and how at certain times of day, those lines intersect with each other. So if we're using a standard algorithm in order to calculate our emissions, and we're doing that during the daytime hours, because the daytime hours are typically when operators are out doing leak detection, then a big leak and a small leak is going to come up as the same size leak. And so what we then did is we took this information and we worked it into a new method that we can use to calculate emissions that works in the understanding of atmospheric stability. And so atmospheric stability, if you're not familiar, is more than just wind speed. So a lot of folks think, okay, well, yeah, no kidding, Kate, if you have higher wind, you're going to see, have less concentration because the wind's going to take the gas away from the surface. So yes, that is the case. But when we look at atmospheric stability, we're talking about this integration between radiation, which has to do with our cloud cover, the temperature differential between the surface and the atmosphere, and then the wind. And so when we put that all together, what we were really able to show is this great influence of that stability on the surface concentrations, and therefore the leak detection capabilities as well. So this has implications to leak detection, because to improve your chance of finding a small leak, you probably want to survey during a low solar irradiance condition. But it also has a lot to do with leak classification. And so leak classification is a process that operators go through to grade a leak either as a grade 1 leak, so that it has a significant impact to safety and the environment, all the way down to a grade 3 leak. And this suggests that maybe revisiting leak locations and measuring them under different conditions to verify that a leak is properly classified would probably be the prudent thing to do. And that this meteorological effect, it could result in a leak misclassification. So maybe giving a leak a lower level of risk, or conversely, a higher level of risk because of not considering the stability conditions on the gas concentrations. And so with our group, we, I'm showing you these pictures that look like one-offs, right? We go and rerun these experiments under a wide variety of leak rates. So I think this one was done for 8 different leak scenarios over a period of probably 50 days in order to capture the right amount of data to show the statistical significance of that. So this is taking all of that data and putting it into one chart to show these higher concentrations at night and the lower concentrations during the day. And then when we take all of that and run it across a wide variety of conditions, so wintertime, summertime, raining conditions, dry conditions, what we show is on average, the ratio between the night and the day is about 1.5 to 1.8 when we look at it holistically, as opposed to one scenario, which is what I was showing you on the previous slide. The next thing I want to talk about is different options that we have for quantifying natural gas leak rates from below ground pipeline leaks. There's methods that are used in industry that are mainly based on a mass balance approach, which makes sense. So if you know where a leak is located and you can use some sort of flux chamber method to estimate that, estimate the emissions from that leak, then that's a great way to do it. What my group was really interested in was how to understand, excuse me, using alternative methods that use equipment that operators are already using in the field to be able to quantify their emission rates from below ground pipeline leaks. So one way that we did that which I'll discuss right now, is using a limited amount of surface data and a limited amount of meteorological data and soil data, work that into an algorithm that was based on a concept of resistance, right? So looking at soil resistance, surface resistance, and atmospheric resistance, and then allowing that to give us an approximation of our underground leakage rates. And so we were able to do that and then able to extend it even further to non-steady underground natural gas leak rates. So the interest in this case would be if we have a known leak location and for some reason we think that that leak rate may change, maybe there is some sort of construction in the area and we want to make sure that the infrastructure doesn't get hit, or maybe it's in a high profile area, many different reasons that we'd want to see if we have any change in that leak rate. And so we worked a method to be able to do that. During this whole process, one of the things that we found that was interesting was looking at the surface and what we're calling the near surface concentrations of the gas. And so what you're seeing here is we ran an experiment where we had a low leak rate that was at about 2 standard cubic feet per hour. And then we increased that leak rate to 4.7 and then increased it again to 6.5. And so we started to look at the surface concentrations and then the below ground near surface concentrations of the methane. And below ground near surface, this was sensors that were put 1.2 centimeters below the surface. So we had 20 sensors, as you can see in this layout in the upper left, and then measured the concentration continuously over time. And so as we expected, the near surface methane concentrations were higher, as you can see in the bottom charts. And the near surface methane concentrations, they expanded quicker than the surface concentrations. The thing that we found really interesting though, so that was kind of our obvious finding, okay, it's our experiment's working. But the thing that we found really interesting was when we looked at the surface concentrations, even going from a low leak rate all the way up to what would be considered a high end of the mid-level leak rate, so 6.5 standard cubic feet per hour. Even when we did that, we didn't see a change. If you look at these top 3 pictures, we didn't see a measurable change in the surface concentrations, but we saw those measurable changes very quickly in the near surface below ground concentrations. And so to show this, there we go. To show this just more holistically at all of the 20 sites, this one's showing the surface and this is showing the below ground near surface concentrations. And the reason that this was of interest to us is because we wanted to work this information into our emission estimates, but then also think about how we can work this into our response to the below ground leak scenarios. The last example that I want to give is a below ground example, but as influenced by the surface condition. And this is an experiment that we ran this past winter where we had a leak at, and when I say a leak, this was rerun 7 different times. So we had a leak in a dry condition, and then we took that exact same leak and then we did all of our measurements under a snow and frozen topsoil condition. And then we did it again under a large rain condition. And what we were able to quantify for the first time was how the surface condition is affecting the speed and the distance that the gas is moving. And so from a safety perspective, this is of great interest to industry. And so for snow and ice conditions, what we saw was that the natural gas spread up to 5 times farther than under the same dry grass covered conditions. And that the methane concentration, it exceeded, LEL is the lower explosive limit, over 10.5 feet from the leak location within 6 hours of the leak initiating. And so what we're trying to do very systematically is demonstrate how the migration distance is increasing over similar timeframes, how that spread is increasing. And then the third part that we found really interesting was the bottom point there, where it says LEL levels persisted 8 days after the leak was stopped. So the persistence, this is hanging around of the gas for longer periods of time. And so that increased as well. And then what we also saw in all of our data that's on, if I blew up this picture on the tail end of figure B, what it shows is how the gas continues to spread even after a leak is fixed. So for example, we would stop our leak and then we'd look at the outer boundary of that leak and how it would continue to spread below ground. That continuation, the spreading is, of course, if you think back to your fluids mechanics class, it's due to diffusion, right? So whenever we have a case where we have a high concentration and a low concentration, the gas wants to move from that place of high concentration to low concentration. So there's two mechanisms below ground. We can either have that movement due to pressure, and so that's often called advective flux, and then we can also have the movement due to that change in the concentration gradient. And so in this case, the leak continues to move because of that change in the concentration gradient. And so one question you may be thinking is, what do we do with all of this information? What we first and foremost do when we find interesting experimental findings, or when we extend them with modeling, is we connect with industry and have them discuss how to integrate this into practice. Some of this work is being incorporated into the PHMSA changes in their regulations for the Pipes Act, and how that can help to increase safety while also decrease emissions into the atmosphere. And we're interested in ultimately being able to develop system level solutions, right, to mitigate the leakage. So I'm hopeful that I'll be out of a job at some point and move on to different research areas, because we have all of this figured out. So our next steps that we have with our work is looking at new and existing solutions to these challenges. And so my group has been moving more into the hydrogen space and looking at hydrogen mixes with natural gas, and how that affects the gas transport behavior, and then the surface presentation of the leak, and then its escape into the atmosphere. And then also lots of different creative approaches, or integrating existing approaches for leak detection. And I'm also open to many other ideas that some of you may have on this call. So feel free to reach out to me if this is a topic that's of interest to you. And I'm always happy to talk about my research and provide more details as well. So I've listed my contact information there, as well as my research website. And I didn't talk about it today, but I'm very passionate about education and science and engineering education as well. And so through another one of my projects, we've developed education resources for K through 12 in both English and Spanish that can be used in classrooms. So that's another effort that I have, and happy to talk to you about that or anything that I presented today. So with that, I'll hand it back to Chris and Mike.
All right. Okay, I guess we got one question. Are there any ribbon type sensors that can be used within pipes to detect pressure drops, or those that could go in trench to detect a particular gas?
Yeah, there are different, am I still sharing? There we go. Stop sharing there. There we go. Yeah, that's a great question. So there are different methods that are used to detect leaked gas. The simplest one is looking at a mass balance, right, from one point to another point. And I often get the question of, okay, why are you trying to detect the gas externally? Why don't we just measure it in the pipeline itself? The issue, to my understanding, is the thermodynamic properties of the gas and how that changes along the supply chain. And so it's changing in its the amount of liquid versus the gaseous form that's in the pipeline that makes it really difficult to do an honest mass balance on gas pipelines. This is easily done for liquid product, but not so simple for gaseous products. That's especially true in distribution type cities scenarios. So it's not as easily done. There's the use of TDR, for example, that look at different changes in, and I'm not totally familiar with all of this technology, but they put them along the outside of a pipeline to look at any changes in the pipe behavior and to try to understand whether or not there's a potential leak. So that has been looked at before. Good question.
I'll see if anybody has any other questions. Let's see, we have one more. How do quantities of gas from underground leaks compare to quantities released from above ground, such as leaks, unignited flares, and intentional venting?
Yeah, that's a great question. I don't have the numbers off of the top of my head on that. But the flaring and venting is I think an order of magnitude greater than what we know about below ground leaks. I think a lot of that is because we've quantified the above ground leaks. We've quantified flaring. We've quantified venting scenarios, both intentional and unintentional. But the below ground, it's the whole out of sight, out of mind issue. So I think that our emissions from below ground are much higher than we have an understanding of at this point. I think that we'll continue to understand that better. And as we find different ways to detect the leaks more efficiently, and then to be able to quantify them. But I think we haven't focused on it. And that's why the estimates are as low as they are.
Great. Don't see any more. I think that's it for the open questions. So yeah, with that, I guess if nobody has any other questions, I just want to thank everybody again for participating in today's ASCE Texas Section technical webinar. I'd also like to thank our presenter, Kate Smits from SMU.